Hi, Mitch Wenger back with another video on data analytics and machine learning. In this video, we'll discuss ways to represent text in data mining. Hope you enjoy. Okay, let's get started. When it comes to pre-processing text, we need to figure out how to convert a document of prose into a feature vector of attributes. In order to do this, we have a number of tools available to help us make things as consistent as possible. First, we can standardize the case. There are situations where case matters, but often we want to treat things like iPhone, lowercase I, capital P, iPhone, all caps, and iPhone, capital I, capital P, as the same word. Plus, we've all seen that person on the forum that has to type everything in all caps, even though everybody keeps telling them they're yelling in the forum. Next, we want to standardize variations of a word: singular, plural, present tense, past tense, future tense, modifier, etc. In this situation, words such as argue, argues, argued, argument, and arguing will be stemmed to something like argue, A-R-G-U. Note that the stem doesn't need to be an actual word. And also note stemming isn't perfect, and there are a number of stemming algorithms available. The Porter approach is one of the most commonly used algorithms, so you may also hear people say that they're portering or porterizing their text. Punctuation and numerals also present challenges. Most basic text analysis ignores both, but it's definitely something you should consider as you evaluate your text mining objectives. Stop words are typically removed from document analysis as well. Now, stop words are those commonly occurring words that you see all the time, like a, an, of, the, and others. Most software tools have a predefined list of stop words that you can use, including variations for different languages, disciplines, etc. You can always customize the default lists, and many sources provide lists of stop words that are tailored to their specific purpose. Sentence fragments are typically ignored for basic text analysis, but we will revisit that concept later. One of the first techniques we typically use with text is what we call a bag of words. Now, this isn't related to mathematical bagging techniques that advanced algorithms use, but it simply refers to the idea that we're taking all the words in a document or in a complete set of documents and throwing them into a bag without regard to sentence structure or word order. Each word simply becomes a feature in our data set that we can use in our modeling efforts. Each document, therefore, becomes a case or an instance in our data set. We often refer to the entire set of documents in our data set as the document corpus. Now, the bag of words is a cheap, easy method for initial text analysis and often gives us all we need. Many spam filters use a bag of words approach as one of their initial algorithms. Now, we've mentioned that each word is a feature, but what is the value of that feature? We'll discuss a few approaches we can use for valuing each feature: tokenization, term frequency, and more. As you might imagine, many words in a document corpus won't appear in an individual document. We'll discuss that in a few minutes. Let's see how tokenization works. Let's say we have the following 3 documents. We can break each document down into its component words, then put all the words in a table and indicate whether that word shows up in each document. This gives us a Boolean value for each word within each document. If we change that Boolean value to a 1 or a 0, we have now tokenized the words in that document. Now, if we update our table to include a count of each word in each document, we are now measuring each feature's term frequency within the document. These are the 2 most basic approaches for valuing text features. Now, term frequency is great for considering how often a word appears in a single document, but it's also important to consider how often the word appears in other documents. How many documents in total does that word appear in? What is its frequency throughout the entire corpus or document list? When analyzing text, the most informative terms are neither too rare nor too common. In a large corpus, a single document will often only contain values for a very small percentage of features in that corpus. As a result, we end up looking for features, that is, words, that appear in multiple documents. If a word only appears once, then it's not going to be useful for finding similarities with other documents. Of course, that term will now be great for a search. On the other hand, if a term occurs in every document, well, then it doesn't really differentiate one document from another. As a result, we usually impose some lower and upper limits on word frequency when we analyze text. We can calculate the sparseness of the various words or terms in our corpus as the inverse document frequency, or IDF. As you can see, it is calculated for any term T as 1 plus the log of the total number of documents over the number of documents that contain the term T. Note that as the denominator gets larger, the log value of the ratio approaches 0, so the IDF approaches 1 as the number of documents containing term T increases. Some IDF calculations dispense with the constant, resulting in a value that approaches 0 instead. Note that the fraction within the parentheses is the inverse of the probability of T in a particular document. We'll see how we can use this in just a minute. Here we can see that the IDF curve indicates the boost a term gets for being rare. So as you can see, those terms that are very infrequent have a high value for their IDF. But as the term approaches 100% of the documents, its IDF decreases and approaches the value of 1. Stop words such as and, or, and the will typically have values at or really close to 1. Now let's revisit the concept of entropy and see how it applies here. You'll recall that the probability of a term T occurring in a document corpus is the number of documents containing T over the total number of documents. It logically follows then that the probability of not T is 1 minus the probability of T. We can calculate entropy for any term, therefore, in the document corpus. If you'll recall our original entropy equation for a partitioned data set, and in this case, we're simply partitioning it on T. It's either T or not T. We can substitute the IDF calculations for T and not T into our entropy equation, giving us the second equation you see here. This calculation gives us the same entropy curve we're used to and has the bonus of being an expected value calculation for T as well. So we've learned about term frequency, we've learned about inverse document frequency. One of the most common ways to represent text is using what we call TF-IDF. And you may have recognized that this is simply a combination of the two terms we just reviewed, and as the name implies, we calculate it by simply multiplying TF for a term within a specific document and the IDF for the term across the entire document corpus. Basically, TF-IDF boils down to how often does a term show up in this document relative to how often it shows up in all documents. Once we have calculated TF-IDF for all the terms in a document, we have a feature vector for that document. We can continue to do this for all documents until we have a feature vector for every document in the corpus. And we can use this transformed dataset to perform classification, clustering, or simple retrieval operations. From here, we can employ a number of our familiar techniques for feature selection, minimum and maximum thresholds for terms, ranking terms using information gain, etc. In our bag of words approach, we'll often use TF-IDF as our measure, but we can also use those simpler Boolean and term count values as well. We can also normalize our measures just like we would for any other approach. At this point, we can proceed with basic analysis using any technique we want. In many cases, we'll use a distance function to determine similarity. This approach, in fact, is a decent starting point for a search engine. That's it for this discussion on representing text. I hope you found it useful. As always, be sure to check out the other videos in this series.